Hello and welcome to our first online lecture / answer key video. So what I'm going to do here is I'm going to go through the questions we would normally do in class and walk through the answers like I would in class. Now, to get the most out of these videos, I highly suggest you look at these problems and you actually try them, look them up in the book, see if you can solve them, struggle with them for a little bit, then come to the video if you're completely lost. If you just go to the video firsthand, copy down the answers and figure you're going to get it later, you're not going to get it later. So you need to put in that struggle to be able to retain this information. Now, if you have any questions about anything that I talk about, anything in the lecture videos that I posted, anything at all, please don't hesitate to reach out to me. I'll be happy to set up a video conference time with you, or if you just want to answer questions over email, we can do that too. Alright, let's get started. So our first question, what is the pressure in a 10-liter cylinder filled with 0.448 moles of nitrogen gas at a temperature of 315 Kelvin. Now, the whole theme for our lecture today is the ideal gas law. And the ideal gas law I have written here. The pressure of a gas times the volume of a gas equals the number of moles of a gas, that's N, multiplied by R. R is a gas constant, and R will always be given to you, multiplied by T. Now, the only tricky thing about PV equals nRT is you have to make sure P, V, N, and T all match the units of the R you're given with. So if we look R, we have liters, our volume's in liters, moles, N's in moles, temperature, K, and we have temperature in K. And we're trying to solve for pressure, and the only unit we haven't touched yet is this kilopascals. So our answer should be in kilopascals. So the only thing that we don't have to modify anything. I was going to say I thought our temperature was in Celsius, but it's in Kelvin already, so we're ready to go. So pressure equals our volume, 10. Or pressure times our volume, 10, equals number of moles, 0.448, times the gas constant, 8.314, times temperature. We want to solve for P, so we just divide each side by 10, and our pressure is 117 kilopascals. This I'm showing on the right-hand side is how the units all cancel out to show that we are actually left with kilopascals. Now, all of the questions we're going to work on today has to do with PV equals nRT. Now I'm just going to change this slide here. This image shouldn't be there yet. Alright. So our next question is that we have a weather balloon inflated to a volume of 28.5 at a pressure of 748 millimeters of mercury, temperature of 28. We let the balloon rise to 25,000 feet. Pressure is 385 millimeters of mercury. Temperature is minus 15 C. If the balloon can expand, what's the volume? And here's our R. We have liters, atmosphere, mole, and K. Now let's check the units we were given. So we're given a volume in liters, that's good. Our pressure is in millimeters of mercury, and our gas constant is in atmosphere, so we need to convert our pressure to atmospheres to match our gas constant. Temperature is 28 C, gas constant is in K, so we need to convert that to K. And the same is true of the other pressure and the other temperature in our problem. Now, I drew a little picture to show what's going on here. So we start at the ground. Here's my crappy weather balloon. And we're dealing with gases, so our equation is going to be PV equals nRT. So pressure, volume, temperature were given, R is given. The only thing we don't have is N. And then we release the balloon in the air. Again, we're given pressure, temperature, but not volume or N. So it's the same balloon. So the N's going to be the same in both on the equations, whether it's on the ground or the air. So we're going to use the variables on the ground to figure out based on what we have written here, how many moles of gas did we fill into this balloon? That's PV equals nRT. So I have to do those conversions I stated earlier. There's 780 millimeters of mercury in 1 atmosphere. If we have 748, that's 0.956 atmospheres. Pressure times volume, which is in liters, equals N, gas constant, and temperature. So go from C to K. You need to take your Celsius temperature and add 273, and you get 301 Kelvin. So PV equals nRT. The only thing we don't have is N. Rearrange to solve for N. So you divide each side by 0.08206 and 301. You found we have 1.1 moles of gas in our balloon. And remember, I said this N on the ground and the N in the air is the same. So now we can figure out, okay, once we're in the air, how does the volume of our balloon change? So the pressure is now 0.494 atmospheres. Everything else is the same. We solve for V, remember PV equals nRT. Volume is 42.9 liters. Question 3. So we need the molar volume of gas at STP. STP means standard temperature and pressure. That is when you're at 1 atmosphere and the temperature is 273 Kelvin. That's STP conditions. Okay, so what is the molar volume of a gas at STP? Or sorry, use the molar volume of gas at STP. Turn the volume in liters of 33.6 grams of neon. So here's our gas constant, liters, atmospheres, mole, Kelvin. All of our units have to be in these, but we're given a weight in grams. So I'm going to convert that to moles by using the periodic table. I look at the molecular weight of neon, see that is 20.2 grams for 1 mole. And so 3.6 is 1.66 moles. Then I do PV equals nRT, pressure is 1 atmosphere, that's good. Temperatures in Kelvin, 273. And I solve for V, and V is 37.2 liters by rearranging my ideal gas law like that. Question 4. What is the density in grams per liters of hydrogen gas at 20 degrees Celsius and a pressure of 1,655 psi? Our gas constants in liters, atmospheres, mole, Kelvin. So we're going to need to change Celsius, and we're going to need to change psi in the atmospheres, and that's how you do it. 1 atmosphere is 14.7 psi. So we're trying to find something that's grams per liter. So we need a volume, and we also need a grams. But if you notice, I didn't tell you how many moles we have, and that's okay. The way a gas works, the more moles you have, the bigger the volume you have. So ideally, you could pick any mole, or you could pick any volume to start with and solve PV equals nRT for a question like this. When I'm looking for a ratio of grams to liters, you can just make up a number and say, okay, let's assume I have 1 mole. What is my volume of that gas at 1 mole? And so that's what I've done here. So here's the temperature going to Kelvin. Here's my psi going to atmospheres. And I just say, you know what? I'm going to say we have 1 mole. So what's the volume when we have 1 mole? So PV equals nRT. Plug in my variables, solve for volume. I get 0.214 liters. Now this is hydrogen gas. Hydrogen gas has the molecular formula of H2. So I look up on the periodic table and find 1 mole of hydrogen gas is 2.016 grams, which means the weight is 2.016 grams. So the density is the amount of grams divided by the volume that I found, and hydrogen gas has a density of 9.42 grams per liters. Question 5. So I have a sample of gas that has a mass of 38.8 milligrams, volume 224 milliliters, temperature 55 Celsius, pressure 886 torr. What's the molar mass? So remember, molar mass is grams per moles. I'm given grams, I'm given a volume, I'm given a temperature, I'm given a pressure, so that's P, T, V, R is given. Now I can solve for N. Once I get the number of moles, I take my weight divided by number of moles, that's molar mass. So again, make sure all your units match your gas law units. So I need to convert milliliters to liters, and I do that by dividing by 1,000, 0.224 liters. I need to take my torr and make it to atmosphere. 866 torr is 1.14 atmosphere. I need to take my temperature and convert it to Celsius. So I take my temperature, add 273, there it is in Kelvin. Now I have all my units ready to go for PV equals nRT. That's here. Solve for N, and I get 0.00949 moles. And I forgot to do the last part here, but to find the molar mass, you would take your mass in grams, which is 0.0388 grams, divided by the number of moles you have, and that will give you molar mass. Question 6. So I have a gas mixture that's made out of 3 gases, nitrogen, oxygen, and helium, and they all have pressures. So what's the total pressure? And what is the mass of each gas in a 1.35 liter sample of this mixture at 25 C? So I'm given a gas constant, which is liters, atmospheres, mole, Kelvin. They're all in torr, so I need to convert them to atmosphere. Whenever you see a torr, that's the same thing as millimeters of mercury. So let's take a look at this. First off, pressure total. All you have to do is add up all your pressures. It's that simple. I don't care if they're in torr or atmosphere, so I just left them in torr. Then once I have my total, I'm going to convert that to atmospheres because I want to figure out how many moles of gas is in my sample. Because I'm given a temperature, I was given a pressure by the total pressure. I'm given a volume, and I have R, so I have 4 variables out of 5 for PV equals nRT. Solve for N, and I find out my mixture has a total number of moles of 0.0315. Alright, now the way that gases work, whatever their percentage or ratio of the total pressure is how many moles they have. What I mean by that is nitrogen, its pressure is 215 torr. The total pressure is 434. So to find the total number of moles, you take nitrogen's pressure divided by the total pressure of your system, multiplied by 0.0315 to see, oh, nitrogen has 0.0156 moles. And I wanted grams, so you just take 0.0156 moles, look up N2's weight on the periodic table, see it's 28 grams for 1 mole. The weight of nitrogen is 0.437. Do the same thing with oxygen, 102 torr divided by total torr. And helium, 117 torr divided by total torr. You're getting moles in each case. From there, using your periodic table, you can solve for grams. So 0.437, 0.2368 for oxygen, and 0.0340 for helium. Question 7. So we're taking a penny, dissolving in hydrochloric acid, and we get a reaction that is 2 hydrogens plus zinc makes H2 gas in aqueous zinc. Now when we dissolve this penny, we collect gas over the reaction, and we're at 25 C, and the volume is 0.951 liters, and the pressure is 748 millimeters of mercury. How much hydrogen did we collect? Now when you're collecting gas over water, which AQ means your chemistry is happening in water, part of your gas is going to be made up of water. So this is just like the previous problem, where we had gases mixing, except now one of our gases is water. So water has a certain pressure at different temperatures. So at 25C, the pressure of gas, water, is 23.78 millimeters of mercury. Look at our constant again. We're in atmospheres for pressure, millimeters of mercury, so we need to change that. Liters is good. Temperature, we need to change, and we're going to be solving for moles. So let's take a look at this. So what I did first off is I just wanted to figure out, okay, what is the pressure due from hydrogen gas only? So we know the total pressure. The total pressure is 748. We know the pressure from water, 23.78. So if I subtract those two, the only gas left is helium, which has a pressure of 742.22. My 7 got cut off there. That's supposed to be 7. Right. So that's how much pressure is from hydrogen. We're going to use that in a second. But first we need to do PV equals nRT. We need to figure out how many moles of gas cost this pressure and that volume at our temperature as stated in our question. So P is 0.984. V is 0.951, and I'm getting the pressure by taking 748 torr, converting that to atmospheres by saying 760 torr in 1 atmosphere. We don't know N, we're solving for that. This is the gas constant, and temperature is 298, 25 plus 273. So we're solving for N, and we see, based on our conditions and using the ideal gas law, the total amount of moles is 0.0383. So we're going to do the same thing where we look at the pressure of hydrogen divided by total pressure multiplied by total numbers of moles, and we'll get how many moles of hydrogen gas, which is 0.0371. Once we have moles of hydrogen gas, we can then use our periodic table to determine how many grams that is. So we look and we see, oh, H2 has a molecular weight of 2.016 grams per mole. So our moles times our weight is 0.0747 grams. So that question's a doozy. You probably won't see something like that on your test. That's just more to really test your understandings. If you can do question 7, there's nothing you should be like. You should ace the next test on gases, because this is a difficult question. It takes a lot of critical thinking and understanding of principles. So if you can do it, you are gold. And we have another question that's similar to this, which combines topics we've talked about previously. So we have a airbag, and this will inflate after an impact. And the impact will give the reaction to sodium azide, or NaN3. We'll go to sodium plus nitrogen gas. So nitrogen is our gas here. If this bag has a volume of 11.8 liters, how much sodium azides, or NaN3, in grams is required to fully inflate this bag upon impact? And let's say we're at STP conditions. STP, which means temperature is 273 and pressure is 1 atmosphere. So 273 K, pressure is 1 atmosphere. So we're good with our gas constant. So we see 1 atmosphere, temperature is 273, volume's 11.8 L. How much N2 gas did we actually make? What is the number of moles? So PV equals nRT. Solve for N. We find out, oh, we have 1.89 moles of N2. Now we want to use stoichiometry to figure out how much sodium azide that is. So if we go back to our previous equation, we see that for every 3 moles of N2 we need 2 moles of NaN3. So we have 1.89 moles of N2. For every 3 moles of N2, we make 2 moles of NaN3. Then we can look on the periodic table and see, okay, 1 mole of NaN3 is 82.98 grams, which means the total weight of the NaN3 you need to inflate your airbag is 104.6 grams. So not that much, but that's how much sodium azide you need in your car. And our last question, not any math. So let's say we have a 1 liter sample of helium gas and a 1 liter sample of argon gas. Room temperature, atmospheric pressure. Do the atoms have the same average kinetic energy? And the answer is yes. So gas, well, kinetic energy is energy of movement. And different gas molecules can have different amounts of this kinetic energy. But if you look at the average, at any given temperature, all gases have the same average kinetic energy. It doesn't matter what they are. Do helium atoms have the same velocity as argon samples? And that's no. So 2 things make up kinetic energy: speed and weight. So the bigger you are, the more kinetic energy you have. The faster you are, the more kinetic energy you have. You can kind of think of it like, I don't know, anything that's projected at you. If a cannon and a bullet are coming at you at the same speed, the cannon's going to do a lot more damage because it is way heavier. All right? Or if an elephant comes at you at 0.1 miles per hour versus a car coming at you at 100 miles per hour, the car is much lighter than an elephant, but that's going to do a lot more damage to you because it's going a lot faster. So that's what kinetic energy is. And based on our previous question, 9a, we said all gases have the same average kinetic energy. So helium and argon, if you look at the periodic table, they weigh differently. Argon's heavier. So the only way these can have the same average kinetic energy if they weigh different is if they also have different velocities. Helium is faster because it's lighter. Last, argon's bigger, so they're more massive. Do they exert a greater pressure? Intuitively, you might think yes. Big things exert greater pressure, but it's not true. This whole problem set, we've been talking about PV equals nRT. Pressure times volume equals number of moles, gas, constant temperature. Not once did we really care what the gas was when using PV equals nRT, because the ideal gas law works for any gas. So no matter what gas you have, you will exert the same pressure if you have the same amount of moles and the same volume and same temperature. Argon, helium, whatever. So we're assuming all gas acts the same, so everything exerts the same pressure on the walls. And that's it for this problem set. Again, please let me know if you have any confusions, any questions. We can either answer those through email, or we can have a video meeting and I would be happy to explain that further. Otherwise, I will see you in the next video.